Hello everyone, today is day 62 of solving a LeetCode problem every day, and today I'm going to solve balanced binary tree. So given a binary tree, determine if it's height balanced. A height balanced tree is a binary tree in which the depth of the two subtrees of every node never differs by 1. So in this case our output is true because if we look at every single node, the difference of the heights of the left and right subtree is always going to be less than 1. So here the difference is 0, and here the difference is 1, so we have a height of 2 and a height of 1. Now here it's going to be false, because if we just look at the root, we see here we have a 1, 2, 3, so we have 1, 2, 3, so 3 nodes here, but only 1 node here. So the difference is going to be 3 minus 1, which is 2, which again is not or in this case it's not balanced, but it was balanced here. So the way you might think to do this right away is a kind of top-down approach. So what you might do is you might take this root node right here, calculate the max height of the left subtree, calculate the max height of the right subtree, compare them, see if it's valid, then move on to the next nodes and do it again. But the thing that would happen with that is you're going to reach a solution that's going to be of quadratic time complexity O of n squared. And the reason why is you have to traverse n nodes and then n nodes again to figure out the height. So for example, here we can figure out the height is 1 since we traversed this one node. Then we got to traverse these nodes over here to figure out the height is 2. And then we see the difference is 1, so this node is valid. Then we have to do the same thing with this and its children, same thing with this and its children, and that's how we get to n squared. But the other approach is a bottom-up approach. So what if instead we started from the leaf nodes and checked that the leaf nodes are valid, and then return the heights back up to their parent nodes? And that's the approach that I'm gonna take. So I'm gonna start from the bottom, and basically we're going to be using depth first search. So let's call we're just going to call it, or we're going to define our function as DFS, and it's only going to take a root. Cool. So now let's think about this a little bit. What do we need to do? Well, first of all, since this is a recursive method, we do need a base case. And our base case is that if the root is none. So we can check if root is none. So if the current root is null, what we're going to do is return an array where the first value is going to be true and the second value is going to be 0. So what I'm doing here is returning an array, and the reason why is that this first value is going to tell us that the tree is balanced, and this second value is going to tell us what the height of the current tree is. So since the root is none, we know that there's no node there, so the tree is balanced there. And we know that since there isn't a node, the height is also going to be 0, which is why we're returning it this way. Now since we're doing a depth first search, we want to search first before doing any type of processing. So we're going to call DFS on the left and right subtrees. Cool. Now what we're going to do is, let's say we get to this node right here. So we traverse, we see that the left node is null, so we return this. The right node is null, so we return that. So here we're going to have true 0, and the same thing here we're going to have true 0. So now basically we want to do two things. We want to update this height so we can send that up to the parent node, and we also want to update if the tree is balanced so we can maintain this value right here. So let's start out with balance. So balance is going to be equal to, first of all, left 0 and right 0 have to be equal, and the reason why is that so the left, if both need to be true, because if one is false, then it means that that subtree isn't balanced, so we can just return false overall, since we know that there's no way for that whole tree to be balanced. So the idea is that both of these need to be true, but we also need one more thing, and it's that even though the left and right subtrees it's like themselves might be balanced. When you add that to the root, so you look at the whole subtree including the root, it might not still be balanced because the difference of heights between the left and right subtrees might be different. So what we're gonna do is we're gonna say and left 1 minus right 1 is less than or equal to 1. And what we're gonna do is we're gonna take the absolute value of this. And the reason why is that the right node, like the right subtree's height might be larger than the left subtree's height. And so we just want to make sure we take the absolute value. So if we get a negative number, we don't really need to worry about that negative. The next thing we need to do is update that height. So what we're going to say is, let's see, we're going to return. So we want to return that array. And the first value is going to be balanced. And then the second value is going to be 1 plus the max between the left height and the right height. So what we're doing here is, let's say we're at this node 7, right? So our left and right are going to be this right here, so true and 0. But now once we return the height of this subtree to the parent, we need to add 1, since we're saying there's now one more node in this tree, or like one more level to this tree. So for example, here we're returning 1 since there's one level, then up here it's going to be 2 since we keep incrementing this. Now the reason we take the max between the left and right subtree is, let me see a good example. So let's see, we're taking the max between the left and right subtree and we're adding 1 to it. So the reason why is, let's say we have this tree, for example, right? So we have this tree right here, or this is actually a perfect example right here. So we have this node 2 right here. So if we look at the left subtree's height, it's going to be 2 since we have 2 nodes. The right subtree's height is going to be 1 since we only have one node right here. Now we're taking the max between these 2 nodes because we want to return the max height to the root, which is 1. And the reason why is if we were to pass in the right subtree's height or return the right subtree's height to the root here, it would think the left subtree's height is only 2, while the right subtree's height of 1 is 1. So now if we do that difference and take the absolute value of it, it's going to be 1, which would say that this tree is balanced. But this tree is not actually balanced because if we look at the left subtree, the height here is 2. So when we return this to the root, the total height is going to be 3. And then this is going to be a height of 1. We take that difference, we see that it's 2. So the tree is imbalanced. So that's why we're taking the max. We want to know the max height, not just any height, the larger height between the 2 subtrees. Cool, so that's going to be our recursive method. But now we actually just need to call it. So what we're going to do is we're going to return DFS. We're going to pass in the root. And then all we care about is that first value, which is the Boolean, which is either true or false. So if I run this now, we see that we got an output true. So, okay, we got true for all the outputs. So let's see what the problem here is. So we got the root, calling the left DFS on the left and right. We're checking if they're balanced here, and that if it's less than or equal to 1, then we're returning balance and 1 plus. Oh, so the reason why is these got to be 1. So if I run this again, it's accepted, and now I submit. Honestly, I don't even know how this worked right here because left 0 and right 0 are booleans. So when you take the max of that and you add 1 to that, I don't know what the behavior in Python is, but I didn't know you can add 1 to a boolean. But anyways, so now we see that the solution works. So the time complexity of this is going to be linear, and the reason why is that we're just processing each node once, since we're maintaining that height reference, or just like we're maintaining a pointer to whatever the height is throughout the recursive method. But this so the space complexity is going to be constant, but one thing to keep in mind is that this is going to take space up on the stack since the method is recursive. Yeah, so I guess one thing you might maybe want to keep in mind is if you don't like this, if this whole array thing looks confusing right here, something you might do is just like say is balanced, and you might say this is true as like a base case, and what you might do is like reference that here, and now you don't have to return this array anymore. You can just return the height itself, which might be less confusing to other people, but I'm just going to do it this way. So yeah, that's my solution for the day.